Hi, we're going to look at bond energies or bond enthalpies from a chemical reaction, and this is a quick way to be able to tell if a reaction is exothermic or endothermic. But first we have to understand something about bond energies or bond enthalpies. There's a table in your textbook. So in the Brown and LeMay edition that we are using this year, so we have the 11th edition, there are the average bond enthalpies in kilojoules per mole on page 326. And so if you look at that chart, what you're going to find is that bond enthalpies for a single bond is less than bond enthalpies for a triple bond. So that really makes sense. In other words, it takes more energy to break a triple bond, say a carbon-carbon triple bond, than it does to break a carbon-carbon single bond. So multiple bonds typically have higher bond enthalpies, or those are just stronger bonds. Also, something to remember about bonding from honors chemistry is that triple bonds are shorter than single bonds. But now, how are we going to use these bond energies or the strength of a bond to determine if a reaction is exothermic or endothermic? Well, let's look at a really simple reaction here. We've got hydrogen, H2, reacting with fluorine, F2, and it's going to give us 2HF. So in this reaction, what I want you to be thinking about now, those reactants, we're breaking the hydrogen-hydrogen bond, we're breaking the fluorine-fluorine single bond, and we're forming two hydrogen-fluorine bonds. And so when we were in the kinetics unit, we said that at the activation energy, at the top of that hill, at the transition state or the activated complex, that is where bonds were being broken and bonds were being formed. And so now we're really going to pay attention to the bonds that are breaking and the bonds that are formed. Remember, we said if we had really strong bonds in reactants, that would slow a chemical reaction down. It would cause activation energy to be higher. So now let's have a look at them. So first of all, breaking bonds will always require energy. And so the enthalpies will be positive. So it's going to take energy to break that hydrogen-hydrogen bond, and it's going to take energy to break that fluorine-fluorine bond. And again, you just look at charts to give you those values. But when you form bonds, it will always give off energy, and so that would be a negative enthalpy. So in the long run, you just kind of look, how much energy did I put in? How much energy did I get back? And if you put more energy in than you get back, it's endothermic. And if you have more energy being given off than what you had to put in, then it's exothermic. And so let's do some real calculations with this. Okay, so for that particular reaction, so let's go ahead and get this written down. We've got H2 plus F2 going to 2HF. And I looked up the bond energy for hydrogen bonds, so really this is what's happening. Hydrogen-hydrogen single bond that has to be broken, and a fluorine-fluorine single bond that has to be broken, and then a hydrogen-fluorine bond that's made 2 times. Okay, so here we go. The bond enthalpy for the hydrogen-hydrogen single bond is 432 kilojoules per mole. And the fluorine-fluorine single bond energy is, the cat just sat on my cheat sheet here. The fluorine is 100, oh, now he's testing gravity, knocking everything off the desk. Okay, so the fluorine-fluorine bond energy is 154 kilojoules per mole. And the hydrogen-fluorine bond is 565 kilojoules per mole. And that's for this one and for this one. Okay, so there is a formula for this, and it's not given to you on your formula sheet, but it should make sense. And the formula looks like this. It is the sum of the bond enthalpies of the bonds broken And then minus, I make a big minus, the sum of the bond enthalpies of bond formed. I don't know why this is writing so weird. Okay, so we can now go ahead and do this problem. So I hope you have these values written down. Now notice that this is the amount of energy it takes to break 1 mole of a hydrogen-hydrogen bond, or kilojoules required to break 1 mole of the fluorine-fluorine bond. All right, so for this reaction, let's go ahead and figure out if this is going to be an exothermic or an endothermic reaction. So here are all these bond enthalpies again, and our balanced equation was, I always have to be looking at my balanced equation when I do this, or I will forget something like that coefficient, which is important. Okay, so this is equal to, so the enthalpy of this reaction is equal to the sum of the bond enthalpies for the reactants minus, big minus sign, 2 times the bond enthalpies for the bonds that are formed. That minus sign is showing that these bonds being formed is releasing energy. Okay, so when I did that math, I got negative 544 kilojoules. So this is another way for us to calculate the enthalpy of a reaction. We could, if we had enthalpies of formation, we could go to the back of the book and do the products minus the reactants, and we're going to get something very close to this based on the bond enthalpies. But what this does, this is just another way of doing it. If we didn't have heats of formation, we could do it this way, or we didn't have enough information to do Hess's law. Using bond enthalpies is another way to do it. What this tells me is that the delta H for this reaction is negative. This reaction is exothermic, and so the reaction profile would look something like this, where we're ending at a lower energy than where we started. All right, now I thought practice is good for something like this, and I came up with what I thought would be the hardest reaction that you'd probably be responsible for. Now, just a couple of mistakes that I commonly see. I commonly see students forgetting coefficients. Okay, now that's not a 0. That's just supposed to be a bullet point that was put in here. Okay, we have methane, CH4. So hopefully you remember your Lewis structures from honors chemistry. That's methane. We've got 2 chlorines. So we've got Cl, 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 Cl. Remember, halogens will never multiple bond, so it's a single bond, and 2 fluorines. So F, 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 F. And that is going to give us this chlorofluorocarbon. This is Freon. I think it's Freon 12, as a matter of fact, used in refrigerants. It's bad for the environment. So here we go. Carbon with 2 fluorines and 2 chlorines. And then 2 HFs and 2 hydro HCl's. Okay, so I drew out the Lewis structure so you can see the bonds that are being broken and the bonds that are being formed. So we are breaking 4 carbon-hydrogen bonds. So you would look up the carbon-hydrogen enthalpies, and that is 413 kilojoules per mole. The chlorine-chlorine bond energy is 239 kilojoules per mole. Fluorine-fluorine is 154. The carbon-fluorine bond, and that's being formed here, and we're forming 2 of them, that is 485 kilojoules per mole. We are forming 2 carbon-chlorine bonds, and that is 339 kilojoules per mole. And the HF Again, we have 2 of these, and we have 2 of these. The HF bond energy is 565, and the bond energy for the HCl is 427. So it's going to be the sum of 4 carbon-hydrogen bonds, so it's 4 times 413, plus 2 times 239, plus 2 times 154, minus the bracket, 2 times 485, plus 2 times 339, plus 2 times 565, plus 2 times 427. All right, so when I do that, I got, for my bonds being broken, I got 2,438 kilojoules were required to break all those bonds. And then the amount of energy that was released by forming all of these bonds, I got 3,600. I don't know what is going on. 3,627 kilojoules. So when I take this, my bond enthalpies for the amount of energy required to break the bonds minus the energy given off by the bonds being formed, I get negative 1,194 kilojoules. Again, this reaction is exothermic. I hope that your writing in your notes is a lot better than my writing here on this presentation. Something's going on with my Wacom board. But hopefully you were able to follow this. If you have any questions, let me know. But again, this formula about bonds broken and bonds being formed, it's not an equation that's given to you, but hopefully it makes sense. All right, we're going to practice this as well. Bye.